Hey guys, and welcome to our tutorial video on the HeapSort algorithm. In this video, we'll take a look at the workings behind the HeapSort algorithm and how we can use it to actually sort a list of numbers, alright? Alright, so I'm going to divide this video into two parts. In the first part, we'll take a look at the full worked and visualized example of the HeapSort algorithm. You'll see it step by step on how we actually create the max heap and how we sort it. Right, and in the second part, we'll take a look at the code for the HeapSort algorithm in Python. All right. Okay, so let's begin. Now, before we actually get into how we're going to create the HeapSort, I want to briefly explain a few things about the heap. So the heap is like a data structure. It's similar to binary trees. Basically, it's constructed out of nodes. All right. Each node is just a value. All right, like 29 or 20. All right, or 8. That's a node. Now the rule is that each node has two children, all right? So these two child nodes are referred to as the left child node and the right child node. Now the rule is that the left child node always gets added first. So when you're creating the heap, you're going to add the left one in first and then the right one. Okay, that's one rule to keep in mind. The next thing to keep in mind is the concept of the root node. So what happens is that there's one node at the top, and then it has two children, and then its two children have children, and then its children has children. So that's basically how the heap is created. So the one at the top, which is the maximum value, that's called the root node. It's basically the largest value in the heap. All right, it's called the root node. If all of these rules are being obeyed, if the root node is the largest, and if each parent is larger than its children, then we call this heap the max heap. All right, so this is the concept of the max heap. So basically what we're going to be doing is actually creating a max heap and then using that to sort the list of numbers here. Okay, so before we actually get onto those concepts, let's actually visualize this current array as a heap. Okay, so the first number here is 29. So let's visualize that like this. This circle here represents the 29 node 29. Now, next one is 20. Now remember, as I said, that the left child node comes in first, all right? Next value up is 8, okay? And then the next is 12. So now, remember one thing, we always prioritize the left node, all right? So we're going to begin from 20, all right? We're not going to add 12 onto 8. We're going to add 12 onto the 20th node, like this, okay? Next up is 38. Okay, now that the left node has been filled up, okay, we can now begin adding values to this node over here, 8. We'll add 17 here, okay? Then we'll add 42. And then there's 22 left over here. So we'll add that to 12 over here, which is the most leftist node here. Okay, so now we have a heap. This is not a max heap because clearly the rules of the heap are not being obeyed, the rules of the max heap. Okay, so that's what we're going to do in the next section. We're going to figure out how to actually create the max heap. Okay, just one thing I want you to keep in mind is that we're not actually doing anything to the array here. Right? We're not actually creating some kind of a data structure here. We're not creating some separate entity. We're just visualizing it through this heap. Okay, the array remains the same. Okay, there's no change to the array as of yet. We're going to be doing that in the next step when we create the max heap. Okay, so yeah. Okay, so this is our current situation. Okay, now when we create the max heap, we always begin from the bottommost node. Okay, an easy way of visualizing this is beginning from the end of the array over here. 22 is the last node we have, and you can see 22 over here. So what we do when creating a max heap is that we check the children of that node. We check to see, are its children smaller than it or larger? If they're both smaller, then okay, that's fine, we'll move on. But if they're larger, then we have to swap them, all right? So we find the largest child node, okay? Like if they're two child nodes, like 10 and 20, we'll find the larger child node and then swap it with the parent node, okay? That ensures we maintain the max heap. So let's begin with 22. we can see that 22 is, it has no child nodes, so let's move on. 42 is next. 42 has no child nodes either, let's move on. 17 has no child nodes either, let's move on. 38 has no child nodes either, let's move on. 12, okay, now 12 has a child, and guess what? It's larger than 12. So what we're going to do is swap 22 and 12. Okay? Now I want you to pay attention over here. You can see in the array that 22 and 12 have gotten swapped. Okay? We're actually just swapping the array here. We're just swapping values in the array. Alright? And we're just representing them through the heap. Okay? It's just in our minds. Okay? So the next thing that's up is 8. Alright? 8 over here. Okay, so we can clearly see that 8 has 2 children and both of them are actually larger. So what we actually do is we check to see which child node is larger. In this case, 42 is larger, so we're going to swap 8 with 42. Alright, and there we can see 42 is now the parent node and 8 is now the child. And we can see in the array over here that actually we swapped 8 and 42. The positions of 42 and 8 have been swapped. Okay. So the next one that comes up is 20 over here. And again, once again, 20 is smaller than both of his child nodes. So we're going to swap it with the larger one, which is 38. Okay? And here we can see 38 is now over here. Okay? So if we were to actually ignore this 29 over here, we can see that the entire max heap rule is actually being obeyed. Look, 38, 22, 20, 12, 42, 17, 8, that's good. Okay, now we have one final step to carry out. We need to swap 29 with the larger child node, and then we get the max heap. So 42 is the larger one, so we'll swap 42 and 29. And here we go. Here is our max heap. Okay, now I actually left these numbers over here just so you would know the order, alright, just so that you don't get confused. Alright, 42 is the first node over here, 38 is the second, 29 is the third, then we begin from here, 22, 20, 17, 8, 12. Okay. Now there's one more thing I want to teach you before we actually move on to sorting, sorting the array, because we're actually half done now, okay? I want to teach you the connection between the array and the heap and the indexes, okay? Now you might think that what does the array's current state have to do with the heap? I don't see any connection in it. You might think that. But there is actually a formula, alright? There's actually a reason behind the array's current state. It's not just some random shuffling that we did. Okay, so the rule is that to find the child node of any node, what you need to do is multiply its index by 2. And then if you want a left child node, you plus 1. If you want a right child node, you plus 2. Okay? So how about we try that right now? I'm going to show you how through this array over here, I can locate each one of these child nodes, all right, for each node. So let's try that for 42. Okay? I'm going to multiply 42 by 0. Sorry, the index of 42, which is 0. All right? So I'm going to multiply that by 2, which gives us 0. And now I want the left child node, so I will plus 1. So I get 1. All right? 2 multiplied by 0 is equal to 0, plus 1 is 1. So I look at index 1, and guess what? There is 38 over here. And if you look at the heap, we can see that 38 is clearly the left child node of 42. So let's try that again, okay? 42, 2 multiplied by 0 plus 2. That gives us the second index, 29. That's the right child node. Pretty incredible, right? Now let's move on and try 38. So 38 has the index 1. So I'm going to multiply that by 2, okay? And then I get 2. And then I'll plus 1 into it, and I'll get 3. So that means that at the third index, we can find its left child node. And we can take a look that 22 is at the third index over here in the array. And if I take a look over here, we can clearly see that it's the left child node of 38. So let's try that again. 2 multiplied by 1 plus 2, that gives us index 4. And we can see the value 20 is over there. And it is clearly the right child node of 38. So yeah, this is the connection between the array and the heap, right? This is what we've been doing. We've been creating this relationship in the array, okay? And we'll use this later in sorting, okay? So let's actually begin sorting the array. Now, you may wonder, how exactly can we sort the array using the max heap? It doesn't make much sense at first, but if you think about it, we have one key piece of information right here. You see 42 up here, the root node? Well, it's the largest element in the array. Now, we can use this information to actually sort the entire array. What we're basically going to do is constantly take 42, or actually take the root node, swap it to the back of the array, and then rebuild the max heap while narrowing the search range to exclude 42. So what we're basically doing is picking the largest value, putting it at the end of the array which is its correct position, because it's the largest value. So in a sorted array, it's going to be at the end, right? The smallest value at the start and the largest at the end. So it's swapping it with the last value, puts it into its correct position, and then narrowing the search range to basically exclude 42. We then rebuild the heap and then find the largest value again, the root node. And then we take that and then swap that to the end of the search range, which is basically the second last value. And then we repeat this process. We rebuild the heap again while excluding the second and first largest root nodes, and then we find the new root node of that new search range, and then we swap that to the end, and we keep doing this over and over again until we've basically gotten a fully sorted array. So let's actually begin doing this now, step by step. Okay, so the first root node here is 42, all right? So we'll swap that back with 12, which is the last value, all right? Pay attention to both the heap sort visualization here, as well as the positions in the array, all right? 42 and 12 over there, all right? So this is what we have. I'm using orange to represent the values and nodes that are currently being changed. So we can see that 42 is now at the end of the heap and 12 is up there. And likewise, we can see that 42 is now at the end of the heap, which is its correct position. All right, so I'm using blue here to actually represent the sorted part. So 42 is now sorted, and that's the sorted part of the array. Now we're going to narrow down our search range from 12 to 8 instead of 12 to 42. And we're going to create the heap using 12 to 8. Now, I've actually excluded the value 42 from the heap. Again, the heap is not a physical entity. We're not actually creating something, so it's just visualization. The 42 is still there, but I'm just removing it so that we just reduce the clutter on screen and actually make things simpler to understand and visualize. Okay. All right. So the goal now is to recreate the max heap using the search range from 12 to 8. All right, ignoring 42. We need to do this to find the next root node so that we move it back to the end of the array, and then repeat this process over and over again until we get our sorted array. All right. So here we are. We swapped actually 12 and 38. If I go back here, you can see that everything else doesn't have children or is already sorted, right? 8, 17, 20, and 22 don't have children. 29 is already in its correct position because both of its children are smaller. And 38 is also perfectly fine, but 12 and 38 are not. So since 38 is a larger node, we swapped 38 and 12 over here, all right? But we're still not done, all right? Clearly, you can see that 12 is smaller than both its child nodes, so we need to fix that. And since 22 was the larger node, we swapped 12 and 22. And now we have our correct heap, right? And also make sure you keep in mind the values changing over here as well, okay? And now we'll actually swap 38 with 8 in the next slide, all right? So you can see that here. We swapped 38 and 8. 38 is actually still over here, all right, where 8 was. But we're not including it anymore because we want to pretend like it's out of the heap, right? It's not actually out of the array. It's just out of the heap visualization, okay? So now we have 38 and 42 in their correct positions. Once again, we'll recreate the heap, all right? swapping 28 and 8, all right, then swap 8 and 17, okay, and then remove 29 as well is gone. Now it's in the sorted part. Now we recreate the heap again, swapping 8 and 22, all right, swapping 20 and 8, okay, heap has been created once more. Let's move 22 and 8 again, swap them, and now we have 22, 29, 38, 42. That's sorted. We are half sorted now. Okay, recreate the max heap. Yeah, okay. 12 and 8. We now have the heap again. Okay, now we'll swap 8 and 20. Okay, so 20 is now sorted over there. And now we have 3 values left. Let's recreate the heap again. 17, all right. We're sorted again. We have the heap, and the max heap. And we swapped 8 and 17 again. 8 is now taking the root node position again. We'll swap it to get the correct root node, which is now 12. We swapped the 2 of them, and we are now fully sorted. We have now completed the heap sort visualization, and we have now achieved a fully sorted array. There are still a few more important details about the heap sort algorithm that I want to discuss, but I'm going to leave that for later. I want to quickly go through the code for the heap sort algorithm. All right. So we have 2 functions here, max heapify and build heap. So let me explain build heap first. All right. So basically, it has 2 for loops. The first for loop starts from n. All right, where n is the length of the array, and it decrements, with -1, with counts of -1. So usually we start from 0, all right, and then we increment by 1. But the thing is, I mentioned this earlier, that when we're creating the max heap, you need to start from reverse, all right. So that's why we're actually, doing things in reverse over here. That's something to keep in mind, all right. So this is actually the part of the code that creates the max heap. The max heapify function here is actually in charge of creating the max heap. Okay, so we'll get into that later, but it's basically in charge of swapping the values and making sure the root node is at the top and the child nodes are smaller than the parent nodes, etc., etc. All right, so the second for loop over here is actually responsible for sorting the array, and you can actually see that over here. This line is the biggest change. Okay, array index 0. What this actually means is the root node, because think about it, the 0th index is actually the first value in the array, and when we have a max heap, the 0th index is going to be the root node, the maximum value. So that's why we swap the maximum value with the ith position over here. All right, and then we recreate the max heap, and then we repeat this process again and again and again. All right, so let me explain the max heapify function first, and I'll also explain this over here, the second parameter. This parameter is actually the index, and this one is actually the partition. I'll explain that in a minute. So let's come over here to max heapify. Okay, so what we do here is first calculate the indexes, okay, of I. I is actually, I mentioned this is the index. This is the index of the current node we are positioned at. Okay, so what we do here is calculate the index of its left child node and the right child node. Okay, and then over here we calculate the largest. Right, these 3 statements over here are actually responsible for determining the largest value. So there are going to be 3 scenarios. Here we have L is less than n in the first scenario. So what is n? Well, n is the length of the array, and we pass it into max heapify over here, and we use this. All right. Now, what is this check used for? Well, you see, sometimes when we're looking at the nodes at the end of the heap, we can actually get invalid child node values or indexes actually. For instance, let's say that the length of the array is 10, okay, and we're checking the 10th value like this. So the index that we get for the left child node is 21. Now the thing is, that doesn't exist. So what we do is actually put this check over here to ensure that, hey, that the left child node is actually less than n, right? Because if it's larger, that means it's invalid. All right. So that's what we do. Now over here in the other condition, we check to see if L is larger than I. If the value at L is larger than the value at I. So if it fulfills these 2 conditions, if L is a valid index and the value at L is larger than the value at I, we assign the largest, we assign the index L to it. Otherwise, we assign I to it. All right, I, which is the index we're currently looking at. All right, what we do over here is then another check. All right, we just compare it against the largest value we picked over here to see if it's larger or not. If it is, then we'll assign largest is equal to R. Over here, finally, what we do is we actually checked to see if the largest is equal to I or not. Because if it is equal to I, then there's no need to swap it, because it's already there. And actually, as this comment over here says as well, this only occurs under two circumstances. All right, one, if the parent is larger than both of his children. All right, because then that means that neither this condition came true, neither did this condition come true either. So that means that the parent is larger. This can also mean that there were no children in the first place, in which case both of these conditions failed. So in either one of these two situations, we don't want the swap to occur. Okay. So if, however, there was a scenario where either there only is one scenario when the children are larger than the parent. All right. So if that scenario occurs, then we swap. Okay, we swap, and then we call max heapify again. This is because sometimes when you swap the values, then the order of the heap actually gets disrupted, and you need to recreate the heap. So then we call max heapify, and max heapify will continuously be called over and over again until the max heap has been created. All right, that's just the nature of the max heapify function. Okay, so I think I've explained that. Now over here is actually where the second parameter actually gets used properly. Over here we just used it as the length of the array, but the real purpose comes over here, where we handle the partition. Now remember how I mentioned earlier that we have to keep reducing the search range? Well, this is actually why we did this. Over here the search range is basically n, which basically means that your search range is the entire array. All right, look at the entire array and create a max heap out of it. But in this one, we want to keep narrowing the search range. So we actually did this in a really simple manner, is that we start from n minus 1 and then we keep decrementing by minus 1. So every iteration of the for loop, we basically decrease the search range by 1, which is actually the same thing we were doing earlier, if you remember, in the slides and the images. Each time we created the max heap and then we swapped the nodes, the root node with the last value. Every time we did that, we basically reduced our search range by 1, right? So this is the exact same thing. Okay, so yeah, this is the end of our explanation actually for the HeapSort code. Now, it's not necessary that this is how you do it, all right? There are actually many ways of achieving something. So you can even make your own code after looking at the logic of the HeapSort, all right? So yeah, besides this, there's just a brief one or two things I want to mention about the HeapSort algorithm. The HeapSort algorithm has a time complexity of n log n, which is one of the best actually time complexities. The worst time complexity you could get is actually n squared, which is with algorithms like bubble sort. All right, n log n belongs to the category of quicksort, HeapSort, merge sort, and etc. There are a few others. So how does HeapSort actually compare to these? Well, HeapSort is actually an in-place algorithm, an in-place sorting algorithm. What this basically does, what in-place actually means, is that it doesn't create any extra array to store the result. It does all of this within the same array. It swaps the values within the array. It doesn't make a new one in which it stores the value. So the thing is about HeapSort is that it's actually not exactly the fastest algorithm out there. Quicksort and merge sort are actually a bit faster than HeapSort. The one thing that HeapSort has going for it is actually its consistency, its stability. It's actually pretty consistent and efficient. It doesn't use much memory. It doesn't create many arrays or anything. It doesn't do a huge number of recursive calls or something, which can actually take up stack memory. So it's actually a pretty simple and compact sorting algorithm, all right? Even if it's not the fastest. There are still tons of other sorting algorithms out there like quicksort, merge sort, insertion sort, radix sort, bucket sort, all kinds of different sorting algorithms, each with their own unique idea and concept behind them. So I really advise you to actually go and check out our other videos, all right? Because this is actually part of an entire series on sorting algorithms. So if you want to actually get updated and be the first to know, I advise you to subscribe to our channel. Otherwise, I'll see you in the next video.